We are now going to evaluate the double integral over dx dA by changing to polar coordinates. D is the region in the first quadrant that lies between the circles x squared plus y squared equals 4 and x squared plus y squared equals 2x. Our first order of business, convert the region into polar coordinates and then draw it. X squared plus y squared equals 4 has the equation r is equal to 2. X squared plus y squared equals 2x. Well, on the left, we can replace x squared plus y squared by r squared. On the right, 2x becomes 2r times the cosine of theta, and so we have r is equal to 2 times the cosine of theta. We're going to sketch the graph of this region. Just a quick little sketch here. And since we are told we're in the first quadrant, we're only looking at the angles between 0 and pi over 2. And even though this is in polar coordinates, since these are circles, I went ahead and put it on a rectangular grid. Now we're talking about, in the first quadrant, the region that lies between the two circles. And so we're going to say inside the outer circle and outside the inner circle. Now, as I already mentioned, theta is going to go from 0 to pi over 2 because we're in the first quadrant. But now it becomes a little bit tricky. How do I figure out the limits of integration for r? What I will tend to do is draw a ray that originates at the origin and just draw it out. The first curve that ray hits is going to be the one with the smaller radius. So we're going to say the green one, the circle that has the equation r equals 2 cosine theta, is h1 of theta. Then the second one it hits on its way out, since it took longer to hit that one, it must have a larger radius. And so I'll call the blue circle r equals 2. That'll be my h2 of theta. With that then, I can see that r goes from 2 times the cosine of theta to 2. And with that, I can set up the integral. Theta goes from 0 to pi over 2. R goes from 2 times the cosine of theta to 2. Our integrand is x. That's going to be replaced by r times the cosine of theta. And then dA is replaced by, what is it? R dr d theta. Even though I could factor r out, I can't express this as a product of two integrals because we have a variable lower limit for r. It's 2 cosine theta. So we'll have to take this as an iterated integral, and we have the integral from 0 to pi over 2 of, well, the integral that we already have, the integrand, I should say, has an r squared. So using the power rule there, we have 1/3 r cubed times the cosine of theta, and we're going to evaluate that from 2 times the cosine of theta to 2, and then still integrate with respect to theta. So that'll become the integral from 0 to pi over 2 of 8/3 times the cosine of theta minus 1/3 times 2 cosine of theta, the quantity cubed, times the cosine of theta. So that's going to give us 8/3 times the cosine to the 4th of theta d theta. Let me move this out of the way so it doesn't look like it's trying to mess with each other. Well, at this point, I'm going to factor out the 8/3. There's no reason to leave it in there in the integral. And we have the integral from 0 to pi over 2, of course, times the cosine of theta. But now here we have this cosine to the 4th of theta. We're going to use a power reducing formula. Cosine to the 4th of theta is the same thing as the cosine squared of theta squared. And the cosine squared of theta is equal to 1/2 of the quantity of 1 plus the cosine of 2 theta. So the cosine to the 4th of theta is going to be 1/4 of 1 plus the cosine of 2 theta, the quantity squared. That's going to equal 1/4 times 1 plus 2 times the cosine of 2 theta plus the cosine squared of 2 theta. And that cosine squared of 2 theta gets its own power reducing formula. I will leave it to you to verify that when all is said and done, our integrand becomes the cosine of theta minus 3/8 minus 1/2 times the cosine of 2 theta. I'm going to run out of room. Minus 1/8 times the cosine of 4 theta d theta. Integrating at this point is pretty straightforward. we have 8/3 times the sine of theta minus 3/8 theta minus 1/4 times the sine of 2 theta minus 1/32 times the sine of 4 theta, all evaluated from 0 to pi over 2. Which looks a little terrible, but when we put either pi over 2 or 0 into theta and find the sine of 2 theta and the sine of 4 theta, in both cases, they zero out. We end up with 8/3 times the sine of pi over 2, which is 1, minus 3/8 times pi over 2, and then putting 0 in place of theta for sine of theta, and 3/8 theta gives us 0 both times. Our final answer, 8/3 minus pi over 2.